Good morning, student. Today we are going to learn about resistive load inverter. After the completion of today's session, you are able to explain the operation of resistive load inverter and derive the equation for VOH, VIL, VOL and VIL. So, resistive load inverter. Here, enhancement type NMOS acts as the driver transistor and the load consists of a simple linear resistor. Let's go to the diagram so it is easier for you to understand. So in the driver, here a enhancement type NMOS transistor is used, and in the load circuit a simple linear resistor is used, that is denoted as RL. Okay, and we have to remember that drain terminal of the NMOS is connected to Vout and the source of the NMOS connected to ground. Means the source and substrate terminals of the driver transistor are both connected to the ground, hence VSB equal to 0. And the Vin is VGS and the Vout is VDS. So, when the input voltage smaller than the threshold voltage of the NMOS, then the NMOS is in cut-off state and does not conduct. As it is not conduct, that means there is no drain current flows through the circuit. So output voltage is equal to VDD, and here IR is equal to ID. And when we apply the Kirchhoff law in the resistive load inverter circuit, then this equation is derived. And as we know, IR equal to ID, so here we replace IR with ID. And at this time the NMOS is in cut-off state, so there is no current flow through the NMOS, so ID equal to 0. And from this equation we can easily derive the ID equation of this circuit, that is ID equal to VDD minus Vout by R. Okay. So, when the input voltage increases beyond the threshold voltage, the driver transistor starts conducting the drain current. So, the driver MOSFET is initially in saturation region, and the saturation drain current equation is this, that is ID equal to K by 2 Vin minus Vt0 whole square, and we know that Vin is equal to VDS, so we replace that term. Then with increasing input voltage, the drain current of the driver also increases and the output voltage starts to drop. For input voltages larger than Vout plus Vt0, or we can say when Vout is less than Vin minus Vt0, the driver transistor enters the linear operation region. At larger input voltages, the transistor remains in linear mode. So, as the output voltage continues to decrease. So, this one is the linear drain current equation. So, the equation is ID equal to K by 2 whole into Vin minus Vt0 into Vout minus Vout square. In place of Vin, here we mention the name VGS, and in place of Vout, here we write VDS. Next, is the VTC curve. Here in the x-axis input voltage is taken and in the y-axis output voltage is taken. Initially, when input is at lower voltage, the NMOS is at cutoff region, means when the input voltage is at minimum value, the Vout is equal to VDD. Okay, until the NMOS is not turned on, and at that time the Vout is denoted as VOH. Okay, then when input is maximum, the output voltage is minimum. Here, when the input is maximum, output is minimum, and the output voltage here is denoted as VOL. Once the NMOS turned on, slow decrease in output voltage start. Here, slow decrease in output voltage starts. At these points, we calculate the slope, this one, slope, that is dV out by dV in. Then we get the value, that is -1. At that point, the input voltage is denoted as VIL. In the second point, also the slope is dV out by dV in equal to -1. Here the voltage denoted as VIH. These voltages are used to find out the noise margin. So, for logic high noise margin, NMH, that is denoted as NMH, the equation is VOH minus VIL. And for logic low noise margin, the equation is NML equal to VIL minus VOH. Okay. Next, here we discuss about the derivation part of VOH, VIH, VOL and VIL. So first is the VOH. As we discussed before, when the NMOS is in cutoff state, there is no current flow through the transistor. At that time, IT equal to 0. After applying the Kirchhoff law, we get this equation. In this equation, we put the value of ID. By putting the value ID, the term becomes 0. So, here we get Vout equal to VDD. And the Vout when the input is minimum is denoted as VOH. So, the VOH equal to VDD. Next is the VOL. Here V in minus VT0 is greater than Vout. So MOSFET is there in linear region. So the drain current equation will be this. And according to Kirchhoff's law, the drain current equation of the resistive load inverter is this. So we compare these two equations. So here we compare these two equations. After solving the equation, we get this one. This equation is in the form of ax square plus bx plus c equal to 0, which is a second order equation. In the first term, a is 1 and x square is VOL square. In the second term, 2 whole into VDD minus VT0 plus 1 by KR is denoted as B and VOL is the X. and the whole last term is denoted as C. So the equation is represented as second order equation. So by using the formula, that is minus b plus minus whole root over b square minus 4ac by 2a, we solve the equation, and after solving the equation we get the equation of VOL. Next, VIL. So when V in minus Vt0 is less than Vout, MOSFET is there in saturation region. So drain current will be this one. This one is the drain current in saturation region equation. And we compare this equation with the equation derived using Kirchhoff's law for the resistive load inverter. So here we compare both the equation. As we don't have the value of Vout, so we have to differentiate with respect to Vin. So we take derivative of both sides with respect to Vin. So dV out by dV in, here also we write dV out by dV in. After solving the equation, at the end we get VIL equal to Vt0 plus 1 by Kr. Okay. Last one is the VIH. Here V in minus Vt0 is greater than Vout. So the MOSFET is there in linear region. So the drain current equation is this, and we compare the equation with the equation derived for resistive load inverter circuit using Kirchhoff's law. Here we compare this, then we take derivative of both sides, and after solving the equation, at the end we get the equation for VIH, that is VIH equal to Vt0 plus Vout minus 1 by Kr. So this is all about resistive load inverter. Thank you.